Hey guys, welcome to my channel, and today I am going to do a basic video on the basics of static equilibrium. Now I'm assuming if you're watching this video you must be new, so welcome. Without further ado, let's just get started. So now I'm going to draw up a problem. So this is the problem. We have a basic beam like this, right? And we have a fixed support. Sorry, not a fixed support, a hinge support, excuse me, and a roller support. And on this end of the beam, we have a force of 10 kilonewtons going at an angle like this. And I'll just put the ratios like this. Excuse me for not the best drawing of the beam, but I hope that the information conveys well. So we have 10 meters and 5 meters. And for the sake of convenience, let's just call this point A, this point B, and this point C. Okay. So how do we solve this problem? We have to first look at a couple things. Sorry, please excuse me one more time. Let's just make this roller like this so it's easier to understand and see for future references. Okay. So how do we approach this problem? Well, I am going to solve it to the best of my ability, and hopefully it will make sense for all of you guys. So the first thing we have to do is look at what exactly is the problem. And the problem is asking to compute the reactions for the beam. Okay? Now, what are the reactions? Well, that's a good question. So what are reactions in the first place? Let's see. So imagine you're pulling on this rope right here. Imagine that's a rope and you're pulling this downwards at an angle and you're applying 10 kilonewtons of force, right? So obviously this beam, if it didn't have any supports, it would go flying into space, right? And obviously we don't want that. And since this beam we're assuming it to not be moving, that just means there has to be something supporting this beam somewhere along in this beam. And that would probably be this and this, all right, at A and B. So next is, how do we know what reactions there are? Well, at the beginning, I made a big deal about, I guess, just having whether it's a fixed or a hinged or a roller. Now, all of these terminologies must be new to some people watching this, so I'll just give a quick rundown of what they are. So the three most common types will go into a bit more detail later, but the three most common types you will see is a hinged support, a roller support, also it can look like this, and finally a fixed support. Now, to understand these supports, we also first need to understand how force is resisted in certain ways. So the basics of static equilibrium is that things cannot fly into space. Now that may sound like a pretty ridiculous way of putting it, but it is actually pretty true, and that's how I really understood this whole thing, right? So imagine you have this beam, right? And let's just go through each one of these supports. So a fixed support means that if you cannot move this beam either in the horizontal or vertical direction, all right? So in other words, your textbook might mention that it resists these forces. In other words, if this is point A, there will be a reaction, right, pulling this way and pulling this way. So the X in the X direction and the Y in the vertical direction, okay? A roller might be different. A roller can only resist force in the direction that is perpendicular to the roller. So just imagine, I don't know, your roller skates, right? If you try to pull it in this direction, it will ultimately do something like this, and it will translate right to left, right? But on the other hand, if you push it like this, it will not sink into the ground or anything like that, right? But as you noticed, there is something else, and that is rotational equilibrium, so to speak. And what that means is basically, if you're keen and you noticed that I drew an arrow here, you might ask, okay, what if the beam suddenly tilts down like this, right? And you would be absolutely correct in saying that a beam would do this, right? It would kind of just spin, right? Which is why typically, you usually have something on both sides, right? It's kind of like holding a pencil here, right? Imagine, using your two fingers and holding the pencil like this, right? And if you applied a force, let's say you had your friend push down on this, right? Hopefully it doesn't spin this way, and if you were holding it onto it in the horizontal direction, if your friend pulled it this way, it wouldn't budge, and it would just be pretty stable. All right, so hopefully that makes sense. That is my very quick crash course on supports, and if you would like to know more, let me know in the comment section below and I'll make a more detailed video on it. So that was a huge tangent, but hopefully you've skipped in the video if you already know that, and good for you if you do. So you're just here to look at the problem. So let me just copy this down right here, because I know it got a bit busy, but we're still trying to find the reactions. Here we go. Okay, so what are the reactions? We need to first, step one is always identify your reactions. Okay, so in this case, what are my supports, right? My supports are this hinged one over here and this roller at B. Okay, so basically what we're going to do is we're going to ask, okay, what do those resist? And if we look back here briefly, right, we can see that the hinged one, it stops all forces being applied in the vertical and the horizontal direction, but it does not stop any rotation, right? And same thing here, except this one doesn't resist it in the horizontal direction as well. So that just means if you pushed it side to side, it would just slide, right? If you pushed, let's say, something here, this would also rotate, right? Same thing with this one, right? I didn't cover fixed support yet, but it's not part of the problem. I'll probably go over it in another problem, excuse me. So, with that being said, how do we solve this problem, right? That's the 5th time I'm asking it, but to first identify your reactions, right? We can see that this is a hinged support and this is a roller, right? So what does that tell us? That tells us that when we apply a force here, right, it's going to not move in the horizontal and vertical direction. And I am just denoting the node as AYAX, the reaction, sorry. And finally, B, how many reactions do you think this has? Right, it has 1, because, again, this one at B does not resist horizontal force, okay? On its own, if this wasn't here, if the one at A wasn't here, it would just slide back and forth, okay? So, with that being said, you have 3 reactions and 3 equations. Okay? Okay, now how do we solve that? Okay? So, finally, if we see this problem right here, right, we have 3 equations. Sum of forces in the y direction equals 0, sum of forces in the x direction equals 0, and sum of moments equals 0. And what this basically says is that things cannot fly through space. Okay? So, the sum of forces in the y direction means it's not flying through space in the y direction. Sum of forces in the x means that the same thing. And really, sum of moments means it cannot spin out of control, right? There always has to be something that is resisting your force. And that is why these 3 equations are the key to finding out the reactions. Let me just make a quick note for you guys. Okay, so first thing we want to do, all right, we probably want to look at this reaction, I mean this applied force right here, and break it down into horizontal and vertical reaction, horizontal and vertical force, right? So in this case, why don't I just start a new page while I'm at it? Whoops. All right. Okay. So, the first step is to break this reaction down. Break the force down into components. And what that means is basically it will be... Whoa. What is the spelling? Get me out of here. I didn't become an English. I'm not a language major. Okay, so what you want to do, the reason why you want to do this is because it will be ultimately easier to calculate with your 3 equations. Okay, so this force. Okay, now if you're unfamiliar with your trigonometry, again, I can briefly explain that to you, but this is a 3, 4, 5 triangle, which which means that if this force is 10 kilonewtons, all we have to do is just adjust it. This is a ratio, okay? So for every 5 units of force we apply this way, there's 3 this way, and there's 4 this way. All right, so to simplify the math, I guess, we can do 10 divided by 5 equals 2, and then 2 times 3 is 6, and that's the horizontal one right here. Okay, same thing with the vertical one is 8. Okay, and if you're confused on that, how I figured that out, I'll probably go into more detail on how to do this in another video. However, you can always use trigonometry, and I believe this angle would work to around 53 degrees, if I am not wrong. Yeah, 53 degrees. So you're always free to calculate it that way. But now, once we have broken down the force into vertical and horizontal components, all we can do is that it is going this way and this way. Okay, so this is 6 kilonewtons and this is 8 kilonewtons. Okay, now here's the tricky part. The tricky part is really with the positives and negatives, but if you just keep them consistent, everything will work out. Let me repeat that again. If you keep it consistent, everything will work out. So in this case, I do this, you can do this a different way, but if we assume everything that's going up is just positive, everything to the right is positive, everything will work out, okay? Instead of going through each step and thinking like, oh, is this positive, is this negative? all we have to do is just set one convention and just roll with it, okay? So, let me just clean this up a bit so I can highlight more things, okay? So, we have these reactions and we have the forces broken up, all right? So the next step would simply be, let me grab a nice color for you. Okay, would simply be just plugging in your equations, all right? So the easiest first thing we can figure out is sum of forces in the x direction, all right? Which just means, and I'm just putting this for notation purposes, and that equals 0 because things are not flying into space, all right? So if we just set up this equation, right, what forces are in this beam that is going left to right? Well, we can see AX is one of them, and the 6 kilonewtons is the other, all right? So very simple. Remember this convention, all right? Just keep it like that. AX, right, that's your first force, plus 6 kilonewtons equals 0, okay? And to solve the reaction, simply solve for AX. So AX equals negative 6 kilonewtons, right? And so negative, in this case, since you defined AX as being positive this way, this just tells you that AX is actually pulling this way, which makes sense, right? If you were pulling 6 kilonewtons to the right, there has to be some sort of 6 kilonewtons going to the left somewhere that is resisting this force, okay? So that is the simple part, but time to calculate the vertical reactions, all right? Okay, same principle. All the forces going up and down must all cancel out to 0, all right? Or must be in some sort of equilibrium, all right? And I see I mislabeled this, so I'm going to change that real quick. This is actually by, okay? So all we have to do is simply say AY, which is the vertical reaction at point A, plus BY, vertical reaction in point B, and minus 8 kilonewtons. All right, this is from the force, okay? And all that add up should equal to 0, all right? Now we have one equation here with two variables, AY and BY. How do we solve this, right? If we just go through the same notions, AY plus BY equals 8 kilonewtons. Well, what are AY and BY? Well, that's a good question, right? And here's where the third equation comes in. Sum of moments, okay? And for this we define counterclockwise equals positive, okay? And this is just an arbitrary convention. I'm sure that some textbooks might define it the other way, but for the video's purposes, we will keep it at counterclockwise equals positive, which means that anything spinning this way is just positive, okay? So the easiest way to look at this really is to say, okay, the thing I'm looking at, this beam, is not spinning into space, right? Why is it not spinning into space? Okay, now to really think about this, right? Think about a door, right? And think about the hinge of the door here, right? At A, right? So let's just imagine this was a door actually, right? If you push here, which I'm assuming that many of you do, the door will swing open, right? However, what if you push it here? Do you think it will require more or less force to push it? Well, it would be more force, right? Because it's just harder to push a door closer to the hinge, right? And if you get really close, it's almost impossible to open the door unless you have some sort of, you've been working out. So basically, that's really the first principle of moments or rotational equilibrium is that the further away you are from some source, right, the more kind of force or energy or rotational force, whatever you like to think about it as, applies, right? So that's the first thing. The second thing, let me just ask you, go back to this door analogy, right? So let's say you apply a force this way, right? Well, going back to what I said just now, I mean, it is pretty far from here, right? But do you think the door would open or close? Well, the answer is no. Why? Because, I don't know, the hinge stops you, right? It literally stops you. It's pushing back, right? You can't open the door when you are applying a force directly, I guess, in line with the hinge, right? So, with that being said, all we have to do is just look at the beam in the exact same way, okay? Let me copy it for a third time. Or was this a fourth? Okay? So, what we can say is that imagine point A right here is a hinge, okay? And since this hinge support or this hinge support allows for rotation, right? We can just assume that this is some sort of door hinge, okay? So, what we can do is we can simply just say sum of moments around A equals 0, okay? I'll put a little A here so you know that I'm talking about A, all right? So, when that basically says if you're pushing on this beam here, right, that there has to be something that is pushing up the other way to not make this whole thing spin into space. And I know I repeated that a lot more times than I should have, but hopefully by repeating it, you'll begin to kind of see what I mean, okay? So let's just work through the problem, okay? So we know that the distance away from this origin will really affect the amount of, I guess, force you need to push in to rotate the entire system, okay? So sum of forces around, sum of moments around A, very simple, set up the equation. So in this case, it would be 10, and we defined counterclockwise as positive. So in this case, here, this reaction is pushing it this way. So it would rotate like this, right? So it's positive. 10 times By, and then the other force, this 8 kilonewtons here, right, is pushing, is pulling down, right? So it would rotate this way, right? And that's a negative. So minus 8 kilonewtons times 15, because that is the distance away from this A point where we are trying to find the moment about, okay? And once again, this just means that if you are pulling this down, this has to push it back up a certain amount. Using a certain amount of force, this reaction at B has to be pushing up, okay? So, with that being said, very simply, this equals 0, right? Because nothing is flying through space, okay? So, with that being said, all we need to do is solve for By, right? So 10 By equals 8 times 15 is 120, so By equals 12, okay? And since this is positive, we know that By is going up, right? So this is 12. And finally, if we just go back to the previous equation, right? If By equals 12, I should clarify that this is the sum of forces in the y direction equation. Remember that we derived this equation a while ago. Okay, so AY plus BY equals 12, so 12 equals 8 kilonewtons, right? And then finally all we have to do is solve for AY, which equals negative 4 kilonewtons. Alright, now to finally clean up the question a bit, right, we have this question, and here we go. So we have solved it, really. It's very simple, right? I think when you get to higher years, this will be quite a bit more intuitive to you, but I've gone into a lot of detail since I don't know exactly where you're struggling on, and I probably just want to help. So AY we found was negative 4 kilonewtons, right? Since we define this as positive, we can just switch the direction, say this is negative 4 kilonewtons, okay? And same thing with this one here, right? AX is negative 6. And BY, finally, we got 12, right? So this will be 12 kilonewtons going upwards, all right? So just take a look, see if everything kind of makes sense, right? I should erase that negative because it's going down anyways, right? So, you know, if someone was pulling this way, right, there has to be something here. If someone was pulling 8 here, right, you know, there's 12 going up here, 4 going down here, and everything makes sense. So an intuitive check, you can just say that is complete. Alright, so this is the first part of, I guess, the static equilibrium series. Now, if you liked, I don't know, you don't have to subscribe, but yeah, I'm just here to help you guys out, because I know that when I was in uni back a few years ago, I didn't really find anything and I was too afraid to ask. So I was searching on YouTube, and hopefully this helped a few people. And if you're studying for exams, let me know how those goes. So of course I'll be around posting new videos, and that's it for this one. So I will see you all later. Peace.